What if I told you that some of humanity's oldest monuments still outsmart our modern tools and methods? From colossal pyramids aligned to the stars to stone circles hauled over hundreds of kilometers, ancient engineers achieved feats that continue to baffle us. In this video, we'll unveil 13 ancient engineering marvels, each proving that innovation knows no era. Stick around, because number 13 will blow your mind. The first ancient engineering marvel on our list is the Great Pyramid of Giza. Imagine standing before a structure so immense and precise that even today's engineers marvel at its execution. The Great Pyramid rises over 140 meters high, composed of roughly 2.3 million limestone and granite blocks, each placed with near-perfect alignment. Built around 2560 BCE for Pharaoh Khufu, this pyramid embodies ancient Egyptians' mastery of planning, organization, and surveying. Yet, how they achieved it remains partly mysterious. Key puzzles center on quarrying, transport, and placement. Fine Tura limestone and heavy Aswan granite had to be extracted, ferried along the Nile, then hauled across the plateau. Hypotheses include massive straight or spiral ramps, internal ramp systems, or even water-assisted transport. Precision alignment to true north suggests astronomical observations using stars or solar methods, but the exact surveying routine is debated. Internally, the pyramid's chambers and corridors follow a precise plan, but recent muon scans have revealed previously unknown voids, hinting at construction features or stresses we don't yet fully grasp. The choice of material, jointing techniques, and casing stones that once formed a gleaming exterior all reflect advanced technical knowledge. Despite centuries of study and cutting-edge methods, the Great Pyramid continues to challenge assumptions about ancient capabilities. Each new finding refines our understanding, but also spawns fresh questions. Did builders adapt methods as construction progressed? Might hidden passages reveal internal construction ramps? Until such puzzles are resolved, the Great Pyramid stands as a testament to human ingenuity and the enduring allure of engineering enigmas. If this marvel amazed you, hit like, subscribe, and ring the bell. Next, we'll journey to southeastern Turkey to explore engineering marvel number 2, the Göbekli Tepe megalithic enclosures. Imagine a hilltop in southeastern Turkey around 9600 BCE, where hunter-gatherers erected massive T-shaped limestone pillars, some over 5 meters tall and weighing up to 10 tons, in circular enclosures adorned with intricate animal reliefs, long before pottery or settled agriculture existed. Göbekli Tepe challenges the assumption that monumental stone architecture arose only after food production. The site comprises multiple stone circles with paired pillars linked by horizontal slabs, carved with foxes, boars, snakes, and abstract symbols. How did foragers organize such projects? Quarrying nearby limestone outcrops would have required levering and hammering tools likely made from flint. Moving heavy pillars upslope suggests sledges or rolling logs, coordinated by dozens or hundreds of participants. The absence of permanent dwellings implies seasonal gatherings. Groups probably converged for rituals, feasting, and construction, then dispersed, indicating a shared belief system strong enough to mobilize labor without centralized authority. Function remains debated. Enclosures may have served as ceremonial centers for ancestor veneration, communal feasts, or cosmological rites. The rich iconography hints at symbolic narratives, yet without written records, we infer meaning from animal motifs and spatial arrangements. Radiocarbon dating shows construction spanned centuries, with successive circles built and intentionally buried, implying evolving rituals or social dynamics. Göbekli Tepe's existence raises some questions. What beliefs underpin the iconography? Why bury enclosures intentionally? Until more evidence emerges, Göbekli Tepe remains a striking testament to prehistoric ingenuity. If this marvel intrigued you, hit like, subscribe, and ring the bell. Next, we'll journey to Bolivia for engineering marvel number 3, Puma Punku's precision-cut megaliths. Imagine standing on the windswept Altiplano near Lake Titicaca, gazing at enormous andesite and red sandstone blocks, some weighing over 100 tons, shaped with such precision that their surfaces are flawlessly flat, edges meet at exact right angles, and complex interlocking joints fit seamlessly without mortar. I'm talking about Puma Punku, part of the Tiwanaku complex in Bolivia, whose master masons achieved stone cutting and assembly feats that still puzzle modern engineers. Key questions begin with quarrying and transport. Andesite blocks likely originated roughly 10 kilometers away, while harder sandstone came from even farther. Moving multi-ton stones across uneven terrain at 4,000 meters altitude suggests a coordinated workforce, probably using sledges, rollers, or earthen ramps. How did these communities source sufficient labor, manage logistics, and maintain precision under harsh environmental conditions? The shaping techniques also intrigue. Many blocks feature complex H-shaped or dovetail joints, straight channels, and smooth planar faces. Microscopic analyses suggest abrasion with sand and harder stone tools, likely using bronze or copper implements as guides, yet reproducing such uniformity across dozens of blocks would demand rigorous templates, consistent measurement systems, and skill passed through generations without written blueprints. How were templates designed and used? Did artisans employ simple yet effective jigs or framing devices to ensure repeatability? Assembly adds further marvel. Once moved, blocks had to be lifted or slid into place within a modular architectural plan aligned to cardinal axes. The absence of mortar implies exact fits. How did builders achieve final adjustments while maintaining overall structural stability? Ultimately, Puma Punku stands as a testament to ancient ingenuity, urging us to explore how societies can achieve extraordinary engineering without modern machinery. If this marvel astonished you, hit like, subscribe, and ring the bell. Next, we'll travel to Lebanon for engineering marvel number 4, the Baalbek Megaliths. Imagine standing at the foot of a monumental podium where colossal limestone blocks, some weighing over 800 tons, form a platform so vast and precise that even modern cranes struggle to handle similarly sized stones. I'm referring to Baalbek in Lebanon, where the Temple of Jupiter's platform showcases ancient engineers' audacity and skill, yet many questions about quarrying, transport, and placement of these megaliths remain unresolved. Key puzzles begin with the stone of the pregnant woman and its neighbors. Enormous blocks were probably quarried from nearby outcrops, then moved a few hundred meters across uneven terrain. How did builders extract such massive stones with limited metal tools? Transport hypotheses include wooden rollers or sledges on lubricated tracks, leveraging large labor forces. Yet coordinating teams to move stones weighing hundreds of tons uphill demands organizational prowess and knowledge of friction reduction beyond clear textual evidence. Placement on the platform adds further intrigue. Setting these blocks into exact alignments, with minimal gaps, implies measuring systems and on-site adjustment methods. Lifting or sliding them into final positions on a raised podium suggests sophisticated ramp designs or earthen embankments, but archaeological traces of such infrastructure are scarce or eroded. How did engineers prevent cracks under immense weight? And how did they maintain stability in a seismically active region? Modern investigations employ 3D laser scanning to map block surfaces and joint interfaces, geophysical surveys to detect buried foundations, and geological sourcing to confirm quarry origins. Each new study refines our understanding, but also highlights gaps. How did ancient builders conceive and execute such staggering tasks? Baalbek's megaliths stand as a testament to ancient ambition, a massive platform that underpins a grand temple, requiring feats of labor, engineering judgment, and social coordination that continue to astonish. If this marvel amazed you, hit like, subscribe, and ring the bell. Next, we'll uncover engineering marvel number 5, the Antikythera Mechanism. Imagine retrieving from a 2nd century BCE shipwreck a bronze device the size of a shoebox, its interior filled with dozens of finely cut gears arranged in multiple planes, an analog computer able to predict celestial cycles, eclipses, and even Olympic Games dates. I'm talking about the Antikythera Mechanism, a testament to Hellenistic ingenuity whose complexity was unmatched until medieval clockwork. At its core lies the remarkable gear trains, differential-like arrangements modeling the irregular orbit of the moon, gear ratios tracking the Metonic cycle and Saros cycle, and additional dials for planetary positions. How did ancient craftsmen design and manufacture such precise gears without standardized templates or modern tools? Microscopic analyses reveal gear teeth cut with hand tools, yet with uniform spacing requiring sophisticated understanding of astronomy, mathematics, and mechanical principles. The integration of these functions into a compact device suggests advanced planning and conceptual design far beyond common instruments of the era. Deciphering its functions relied on high-resolution X-ray and CT scans, revealing hidden inscriptions that describe usage and calibrations. These texts hint at a tradition of such devices, though no other examples survive. The mechanism's existence raises questions. Was it a one-off demonstration piece, or part of a workshop tradition? How widespread was this technology, and why did it vanish from the record after antiquity? The Antikythera Mechanism stands as a singular window into Hellenistic science and engineering, a compact mechanical model of the heavens demonstrating deep integration of observational astronomy, mathematics, and craftsmanship. Its discovery continues to inspire research into lost technological traditions and reminds us that complex machines existed far earlier than once believed. If this marvel astonished you, hit like, subscribe, and ring the bell. Next, we'll explore engineering marvel number 6, Mohenjo-daro's urban drainage and sanitation system. Imagine strolling through a Bronze Age city around 2500 BCE where every house opens onto a covered brick-lined street drain, each dwelling equipped with a private bathroom and connections to a city-wide sewer network. Mohenjo-daro's urban planning in the Indus Valley civilization set a standard in sanitation unmatched in many later societies. Its builders arranged densely packed neighborhoods with narrow lanes, built uniformly sized baked brick drains, and installed inspection holes and soak pits, demonstrating an advanced understanding of public hygiene and water management. Key puzzles include the organizational framework. How did city planners convey and enforce uniform construction standards across thousands of homes? The absence of deciphered texts leaves us inferring governance from archaeological patterns. Possibly communal councils or elite administrators oversaw labor and resources to build and upkeep the system. Technical aspects also intrigue. Drains had gentle gradients for gravity flow, covered slabs to prevent debris clogging, and manholes for cleaning. Houses featured built-in toilets draining into brick conduits, with chutes leading to underground channels. Rainwater management was tied into the design, preventing flooding in monsoon seasons. Constructing such a network required surveying skills to maintain consistent slopes, knowledge of hydraulics to avoid stagnation, and durable materials resistant to erosion. Modern investigations use GIS mapping of excavated drains, hydraulic modeling to test flow efficiency, and analysis of brick composition to understand manufacturing techniques. Yet questions remain. How were maintenance duties organized across households? Did specialized workers clear blockages, and how often? What cultural beliefs underpinned such emphasis on cleanliness in a time before germ theory? Although Mohenjo-daro's decline saw the network fall into disuse, its remains continue to inform modern engineers and archaeologists about ancient urbanism. If this marvel of early urban engineering intrigued you, hit like, subscribe, and ring the bell. Next, we'll examine engineering marvel number 7, Egyptian obelisk quarrying, transport, and erection. Imagine massive granite shafts, each carved from Aswan quarries weighing hundreds of tons, destined to pierce the sky before a temple's entrance, yet cut, moved, and raised without cranes or steel. Egyptian obelisks, such as those later moved to Rome, embody ancient mastery of stoneworking, logistics, and organization. Quarrying likely began with locating a suitable granite seam at Aswan. Artisans probably outlined the obelisk shape on the bedrock, then used dolerite pounders and copper or bronze chisels with abrasive sand to carve trenches around 3 sides. Wooden wedges driven into grooves and soaked would expand, fracturing the stone. Extracting a single monolith demanded precise planning to avoid cracks, ensuring the column's integrity. Once freed, the obelisk had to travel roughly 100 kilometers to the Nile's edge. Workers likely used sledges on lubricated tracks, coordinating large teams to haul the weight slowly downhill. At the riverfront, seasonal inundation allowed loading onto custom-built barges. Engineers would have had to balance buoyancy and stability, ensuring safe passage southward during high water months, while navigators managed currents and tides. At the destination, often a temple precinct, unloading and overland movement to the erection site likely required ramps and rollers. Surveying ensured alignment with temple axes and celestial references. Organizing labor, provisioning food and tools, and maintaining precise measurements without written technical manuals reflect a sophisticated administrative system. Each obelisk stands as a testament to Egyptian expertise in geology, hydraulics, mechanics, and project management, demonstrating how ancient builders turned colossal stone into enduring monuments. If this feat amazed you, hit like, subscribe, and ring the bell. Next, we'll explore engineering marvel number 8, the Pantheon dome and Roman concrete technology. Imagine entering a vast circular hall under a coffered concrete dome more than 43 meters in diameter, with a central oculus streaming sunlight onto polished marble floors. I'm talking about the Pantheon in Rome, completed around 126 CE. Its unreinforced concrete dome remains the largest of its kind, showcasing Roman mastery of materials and structural design that still challenges modern engineers. Central to this marvel is Roman concrete, made from volcanic ash, lime, and aggregate. Builders varied the aggregate size and composition in successive layers. Heavier travertine near the base and lighter volcanic pumice toward the top, reducing weight and controlling thermal expansion. This gradation, combined with volcanic ash's hydraulic properties, yielded a durable, cohesive material that set underwater and resisted cracking over centuries. The dome's geometry further mitigates stress. Coffered recesses carved into the interior reduce mass without compromising strength, while the oculus, an 8.8-meter aperture, lightens the crown and provides natural illumination. Underneath, the drum's thick walls contain relieving arches and niches, distributing the dome's load evenly to the foundations. Precise formwork would have guided concrete pouring in concentric rings, requiring wooden molds and scaffolding coordinated by skilled overseers. Construction logistics illustrate complex project management. Surveying tools and empirical knowledge allowed alignment of the dome's center with the building's axis, while the oculus orientation considered light and ritual use. Modern analysis confirms the Romans' deep understanding of concrete chemistry and structural behavior. The Pantheon's continuous use for nearly 2 millennia testifies to its resilience. As we study its composition and design, we uncover lessons in sustainable construction and adaptive engineering, reminding us how ancient techniques can inform modern practice. If this marvel fascinated you, hit like, subscribe, and ring the bell. Next, we'll examine engineering marvel number 9, the Dujiangyan irrigation system. Imagine a river engineering scheme over 2,200 years old that controls flooding and channels water without a traditional dam. The Dujiangyan irrigation system in Sichuan, China, designed around 256 BCE by Li Bing, diverts the Min River to irrigate the fertile Chengdu Plain while preventing destructive floods. Its genius lies in hydraulic principles and sustainable design that remain in use today. Rather than blocking the river, engineers carved a fishmouth levee to split the flow. One branch guides water into irrigation channels, the other carries excess downstream. A flying sand weir upstream manages sediment. The bottleneck channel, narrowed by rock cut, increases water velocity, scouring sediments and maintaining clear channels. Combined, these features balance seasonal floods and dry season irrigation without large reservoirs. Construction would have required precise surveying to position levees relative to river dynamics, understanding of seasonal flow variations, and coordinating labor for massive rock-cutting tasks. The system's maintenance implied organized community involvement under state oversight. Its resilience against earthquakes and fluctuating flows reflects deep empirical knowledge of local geology and hydrology. Modern studies use hydrodynamic modeling and sediment transport analysis to understand Dujiangyan's performance and inform contemporary flood control. Remote sensing and field surveys reveal that the system evolved through successive modifications, which improved efficiency while preserving core principles. UNESCO recognition highlights its cultural and technical significance, illustrating how ancient innovation can guide sustainable water management today. Despite centuries of environmental change and technological evolution, Dujiangyan continues to supply water for millions of hectares of farmland, demonstrating a balance between human needs and river ecology. Its design teaches modern engineers about working with natural forces rather than against them. If this ancient hydraulic marvel inspired you, hit like, subscribe, and ring the bell. Next, we'll journey to Jordan to explore engineering marvel number 10, Petra's Nabatean water management and hydraulic engineering. Imagine a settlement carved into rose-red sandstone cliffs in an arid desert, yet sustained by intricate water systems that harvest scarce rainfall and flash floods to support a thriving city. Petra, the Nabatean capital, exemplifies ancient ingenuity in hydraulic engineering, enabling urban life in one of the driest regions of the Levant. At its core are rock-cut cisterns and channels, Runoff from seasonal rains is collected via networks of stone gutters and buried ceramic pipes, funneling water into large subterranean cisterns carved beneath plazas and terraces. These reservoirs, sealed with waterproof plaster, store water for dry months. Overflow and excess floodwaters are managed by dams and diversion channels upstream, safeguarding the city from destructive surges while capturing sediment-free water. The Nabateans also built small check dams and retention basins in wadis to slow flow, encouraging infiltration that recharges groundwater and feeds springs. Ingenious terrace agriculture on surrounding slopes benefited from controlled irrigation, supporting orchards and gardens that moderated local climate and provided food. Ingeniously placed channels guide water to rock-carved troughs for livestock and to public fountains, demonstrating planned distribution. Surveying and construction would have required precise alignment of channels across uneven terrain, carving through bedrock with hand tools, and maintaining gentle gradients to avoid erosion or stagnation. Coordinating labor for seasonal repairs and cleaning of cisterns and channels implied organized administration, likely overseen by Nabatean authorities or guilds. Modern studies employ hydrological modeling and archaeological surveys to map hidden channels and assess capacity. Despite centuries of abandonment, many cisterns and dams remain intact, attesting to durable materials and design. Petra's water system showcases the ingenuity of its ancient engineers, who developed a sophisticated network to harness scarce desert water resources. They skillfully captured and stored rainwater from occasional downpours, controlled flash floods, and distributed water fairly among the city's inhabitants. Each channel and reservoir carved in stone reminds us of the Nabateans' deep understanding of local geology and hydrology. If this desert hydraulic marvel captivated you, hit like, subscribe, and ring the bell. Next, we'll examine engineering marvel number 11, the Parthenon's optical refinements and precision stonework. Imagine approaching the Parthenon on the Athenian Acropolis around 438 BCE and noticing that, despite its rectangular form, nothing appears perfectly straight or level. Subtle curves and leanings correct optical illusions, creating a sense of perfect harmony. This temple to Athena exemplifies ancient Greek mastery of geometry, aesthetics, and stone craftsmanship, employing optical refinements and precision carving that continue to fascinate engineers and architects. Key refinements include the slight upward curvature of the temple's platform or stylobate, bowed about a few centimeters toward the center, preventing a sagging appearance when viewed from a distance. The columns feature a subtle curve, known as entasis, which is a slight bulge in the middle of the shaft. This design element helps to create a visual correction, making the columns appear straight and uniform to the eye, rather than concave. Corner columns are marginally thicker and spaced more closely to maintain visual uniformity under changing light. The intercolumniation and column heights also vary subtly to ensure that rows of columns look straight despite perspective distortions. Executing these refinements demanded precise surveying and mathematical planning. Architects, ictinos and calicrates, likely used string, plumb lines, and sighting rods to lay out curves on the marble stylobate. Calculating entasis profiles required empirical knowledge. Corners, entablature, and sculptural elements aligned seamlessly, reflecting meticulous measurement and quality control without written blueprints. Such precision ensured structural stability and aesthetic impact. The subtle curves also helped water runoff and reduced glare under bright sun. Modern analysis uses 3D laser scanning and photogrammetry to quantify these refinements, confirming the tiny magnitudes of curvature and column adjustments. The Parthenon's enduring presence, despite earthquakes, weathering, and human damage, attests to both the structural soundness of its design and the timeless power of its optical artistry. If this fusion of art and engineering inspired you, hit like, subscribe, and ring the bell. Next, we'll reveal engineering marvel number 12, Ziggurat foundations at Ur on soft alluvial soils. Imagine erecting a massive stepped temple, rising several tiers high on the soft, waterlogged sediments of Mesopotamia around 2100 BCE. The Ziggurat of Ur demonstrates how ancient engineers stabilized immense mud-brick structures atop an alluvial plain prone to flooding, settlement, and shifting soils. Key to this feat was creating a layered foundation that distributed weight and managed water. First, builders probably selected a site above seasonal flood levels, then laid successive courses of compacted fill, creating a broad, leveled platform. This core was likely reinforced with reed mats or bundles interspersed in the fill to improve cohesion and limit lateral spreading. Probably around the base were drainage channels that diverted runoff, preventing water accumulation under the platform. The foundation fill was likely rammed in stages, allowing earlier layers to settle before adding more weight. On top of this prepared base, craftsmen built thick mud brick walls for the ziggurat's core, with outer faces protected by baked bricks set in bitumen mortar to resist erosion from rain or irrigation. The stepped form itself reduced lateral pressure on lower levels, and the broad lower tiers minimized concentrated loads. Regular maintenance was integral, implying organized labor and knowledge of seasonal cycles affecting brick durability. Despite the lack of written engineering manuals, empirical understanding of local soils would have guided these decisions. Builders likely recognized that simple vertical piles would fail in soft ground, so they spread the load over a wide area. Archaeological studies using soil analysis and remote sensing confirm layered construction and drainage remains. While precise techniques remain partly speculative, the enduring remnants of the ziggurat testify to effective ancient problem-solving. If this ancient foundation engineering intrigued you, hit like, subscribe, and ring the bell. Next, we'll explore engineering marvel number 13, Stonehenge's megalith arrangement and transport. Picture yourself on the windswept Salisbury Plain around 2500 BCE, witnessing communities laboriously transport massive stones from distant locations. These stones were then carefully positioned in concentric circles and precisely aligned with the solstices. Stonehenge stands as a testament to the remarkable engineering skills of the Neolithic people, who achieved feats of transportation, precise placement, and astronomical planning with surprisingly limited technology. Transporting bluestones likely involved moving heavy slabs over rugged terrain. Hypotheses include dragging on sledges over greased wooden tracks, using log rollers, and possibly rafts along waterways. For Sarsens, teams likely levered stones onto sledges, navigated river routes, then hauled them overland via coordinated manpower. Archaeological advances enrich our understanding, but also highlight gaps. Exact routes remain partly conjectural, and social structures organizing labor are inferred from settlement evidence rather than texts. Stonehenge's enduring presence testifies to Neolithic communities' capacity to mobilize resources, manage complex tasks, and integrate astronomical observation with communal ritual. While modern experiments approximate transport and erection methods, the full social, logistical, and symbolic dimensions of this megalithic enterprise continue to inspire research and wonder. If this prehistoric engineering astonished you, hit like, subscribe, and ring the bell. Thank you for joining our exploration of ancient marvels.